So up until now, our entire understanding of mathematics has revolved around concepts of arithmetic, the four essential operations, addition, subtraction, multiplication, and division, and algebra, the use of variables in conjunction with those operations to solve problems and create functions. Today we move past those into the realm of the transcendental functions. No, not those kinds of transcendental. A transcendental function is simply one which cannot be composed of a finite series of algebraic operations. They still work perfectly well from a mathematical perspective, they just aren't technically algebraic or polynomial expressions. We start with the exponential function, a function of the form f of x is equal to some base b raised to the xth power. In this case, the variable x actually determines the operation, the number of times that said base b is multiplied by itself. Let's have a brief recap of the rules of exponents. A number, that would be the base, raised to a certain value, the exponent or the power, is that base multiplied by itself so many times. 2 to the fourth power is 2 times 2 times 2 times 2, or 16. Any value except 0 raised to the 0th power is 1. There is some dispute among mathematicians as to what exactly 0 to the 0th power is, but we'll leave that alone right now. Any value to the power of negative 1 is that value's reciprocal. The rules proceed logically from these starting points. With an exponential function, we start with a particular base, a number that is to be multiplied by itself so many times. The base must be a positive number. The result of a negative number raised to a certain power flips between positive and negative based on whether the exponent is an odd or even integer, and the behavior between those integer values is undefined, which leads to no end of confusion, so let's stay positive, literally. That said, any positive base can be raised to any real number exponent. An exponential function is a continuous function whose domain is all real numbers. The form of the graph of the function depends on the base. If the base is greater than 1, the graph approaches 0 for negative values of x and goes to infinity for positive values of x. Think of powers of 2. 2 to the first is 2, 2 to the fifth is 32, 2 to the negative third is 1/8. If a base is between 0 and 1, the opposite is true. Large negative exponential values will go to infinity, while large positive values will close in on an asymptote at 0. 1/3 to the negative second is 9, while 1/3 to the third is 1/27. While we can have 1 as a base, doing so simply implies multiplying 1, or the reciprocal of 1, which is still 1, by itself a specified number of times, which will always result in 1. The exponential function with 1 as the base is a constant 1, and the graph of the exponential function with 1 as the base is simply a horizontal line at y equals 1. You may have noticed one commonality to each of these so far. As noted earlier, any base raised to the 0th power is 1. Therefore, absent any manipulations and transformations, all graphs of exponential functions will cross the y-axis at 0, 1. Manipulations and transformations can be applied to exponential functions in exactly the same way as they were applied to algebraic functions, with essentially identical results. A number added to or subtracted from the variable shifts the graph to the left in the case of x plus n, or right in the case of x minus n. A number added to or subtracted from the exponential expression shifts it up or down. A multiplier dilates the entire graph, stretching it or shrinking it accordingly, and a negative mirrors the whole graph about the x-axis. One of the most common applications of an exponential function is in the calculation of compound interest. Given a certain principal amount, a certain interest rate, and a specified compounding period, we can calculate the resulting amount over the course of repeated compounding episodes. For example, let's take $5,000 and lock it into a certificate of deposit which pays 6% interest annually, compounded monthly. The term of the certificate is 5 years. How much will be paid out at the end of that 5-year term? The formula for compounding interest is a well-known standard form. P is 5,000, R is 0.06 because we need to convert from percentage to a decimal, N is 12 because we will have 12 compounding episodes over the course of each annum, and T is 5 years. The result is 5,000 times 1.005 to the 60th power, and yes, please get your calculators out and follow proper order of operations. At the end of the 5 years, we will have $6,744.25 in the account. As noted before, an exponential operation is a continuous operation. It is also one-to-one. Each value for x relates to exactly one value for y, and vice versa. This implies that the exponential function has an inverse, which it does and which we will cover next when we talk about logarithms.